Okay, so we have how many joining us today? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9, 10. So wait, Rachel, good afternoon, Rachel. Hopefully everything is good with you on that. Okay. So let me see if I can just use PowerPoint so that I can see everybody as well, besides not just myself. Okay, I'm using two screens, but I'm let me see if I can just use the slides instead of the PowerPoints, because for the PowerPoints, when I try to put in the full slide mode, then the full screen mode, then what happens is that it's covering the two screens at the same time, so it makes it difficult for me to see whoever comes. Okay, so let me go into try this week 2 for. Okay, let me try to open this PDF in the Adobe Acrobat. Okay, so this one is the one that I think I already cover up to that linearization, linear systems. I think until here. Okay, so let me just put full screen mode in here. Okay, guys, you can see my screens, right? I just want to reconfirm again. Okay, so last week we have covered introductions to the process control. Okay, so we basically see the what process control is being used for, and then we also go into a little bit into the manipulated variables disturbance, and then into the control variables, and then all these kind of variables. So we go and we give you some examples how you differentiate those manipulated variables, disturbance variables, okay, the control variables, okay, and then we give you also a taste or a flavor of how actually process control is being applied to optimize the chemical engineering systems. In this regard, it's basically a hybrid of the membrane with the polymer electrolyte membrane fuel cell. So it's membrane desalinations with polymer electrolyte membrane fuel cell. So in that project we use Simulink, okay, to simulate the systems, and then we have two layer systems, which is the PID and the model predictive control. Okay, we will not cover the model predictive control, of course, in this process control, because that will be a higher concepts for the process control. But at least you need to be able to deal with the basics process control, which is the proportional, integral, and derivative controller. Okay, so in this second week, we basically cover the modeling, how the mathematical modeling is useful to uh, to be able to model your systems, and then we go into the linear systems. Okay, when I showed you last week and in your project 1, what you will cover is basically a nonlinear systems. Okay, that is nonlinear because we have several terms that are not nonlinear. Either they are in square roots or they are multiplications of two different variables that makes them nonlinear. Okay, but for the concepts, we try to go into the linear systems because the linear system is already established, and it's more easy to be understood. Okay, so we have gone with the linearizations of nonlinear systems with one variable. So linearization is quite straightforward. What we need to do is just to take the nonlinear functions, expand them in Taylor series around the steady-state value, and neglect all terms after the first partial derivative. So let's assume we have a nonlinear function f of the process variables x. That is fx. So this x can be level or temperature or flow rate. Okay, it can also be concentration. It can be anything that you want. Okay, we will denote the steady-state values of this variable as x naught in here. Okay, then what we show in here is actually the Taylor series expansion in here. Okay, so if you have an infinite terms for this series, it's basically approximating the same with this fx in here, or this fx in here can be approximated by infinite terms of this Taylor series. Okay, so that's consisting of this fx naught plus the first derivative term, the second derivative term, and so on until the end derivative term, right? If we neglect all terms of order 2 and higher, we get the first order Taylor approximation of the function as this one. So we don't really care so much about the second and the third and all the other and order higher terms. We only care about up to the first order Taylor expansion of the function. So this is what we need to do if we want to linearize this term. Okay. So now the next one is this. So this is what you can see. If you have the real functions of this fx, it may be something like it doesn't have to be curve. Okay, in here just for the sake of representation, we took it as something that has the curve function. But what we mean when we linearize is that we linearize it around a value. So in here is x naught in here. Okay. So in the representations of this fx naught is basically that value in here, fx naught, okay? And then imagine that we have a slope. So the slope is the f over dx at x naught. So basically what we are taking with this term in here is this representations of this slope in here, okay? We are adding this value in here plus the slope multiplied by the incremental of whatever the value in here, x minus x naught. So if we took it in here, that means our approximations will be located in here, okay, at this particular position. Whereas our real actual values of the fx at this particular point, for example, will be in here. Okay, so at this particular point in here, okay. Then approximations will be equal to, if we took it at this particular point, that will be equal to this particular point in here. So there will be an error, but as long as if we don't really operate far away from this x naught value, then we should be okay. Okay, because we don't really want to operate far away from this x naught anyway. So if we just want to operate close to this point x naught, then linearization will do just fine. Okay. Now, that one that we showed you just now in here, okay, this is for one variables. What happens if we have two variables, two independent variables? So we have x1 and x2. So what we need to do is the same. We just took the first one, and then we just stop it up to the first derivative. But since we have two derivative term for the with respect to the first with respect to the variable. So this one is with respect to the first variable. This one with respect to the second variables. Okay. So what we need to do is we just need to retain these three terms in here, right? And then we need to take that expansions into around the points of x1 naught and x2 naught. Okay. Now, so this one is what it is, and then because we already show you for one variables, and then we show you for two variables, and the same thing that can be applied for the three variables, for the four variables, five variables, and so on, basically. Okay, everybody get it clear up to this point? Anyone I want to ask something up to this point of time? Is Jason around? Normally Jason likes to ask questions, so I'm happy if you want to ask anything. You see, you want to ask something, or this is clear? Basically, no nothing in here, right? Then we go into an example of nonlinear system. So we give a lot of examples here to make it easy for you to understand. So let's say we consider the following liquid system. The total mass balance equation is as follows. So A dH over dt is equal F1 minus F naught. So this one will be the flow rate. Okay, you need to deduct this the unit from this thing. So this A in here, on inspection we will know that this one will have a unit of meter square, or it can be a feet square. Then this dH will be the height of the liquid, since it is divided by the time, so we know that this will be having a unit of meter per second. So imagine that meter square multiplied by meter per second, so that we will have meter cube per second, right? Basically, so the flow rate will have to have the same unit on the right hand side. So this is supposed to be meter cube per second. So if we go back to our process modeling or the process control slides on top, then this will be the accumulations which is equal to the inlet minus the outlet, minus the out, basically. Okay, we will have an accumulations as long as our inlet rate is not equal to the outlet rate and vice versa. Okay, so let's assume that for the case 1, if the outlet flow rate is linear functions of the liquid level, so we can just take this kind of expression and plug it into this F0. Okay, then we can move this term into the left hand side. So this is a linear differential equations because we don't see any nonlinear terms on the edge. Okay, so no approximation is needed. Now, if the outlet flow rate is proportional to the square root of the liquid levels, so if it is the square root of this multiplied by a constant called beta, then we can move it into the left hand side. The resulting mass balance yields a nonlinear dynamic model. Okay, the nonlinear term in the equation is given by this b multiplied by the root square of h. Then we need to use a Taylor series expansion. So we want to basically convert this one into a linear form, into its linear form. Okay, so what we do in here is we put in fx0. So we linearize around h0 or the steady state basically. So we need to differentiate this with respect to the h and then put in h0. Okay, we only interested up to the first value. We are not interested onto the second value in here. Okay, so what you need to do is after you differentiate these things, then you plug in the value of the h0. Okay, basically you know that the derivative of the root square of the h will be half multiplied by the h raised to the order of the minus half. Okay, that's why these terms come in the, instead of coming on the numerator, it's come on the numerator, it comes on the denominator term in here. Okay, so we just put this thing in, and this term in here becomes two terms in here, becomes this, right? Then we can readjust, we can just manipulate. We for example, this term in here, we leave it in here in the left side. Okay, and then the term in here, we move it into the right hand side. Okay, this one move into the right hand side, and then the second term in here is also move into the right hand side. Okay, and this term with this term is actually the same. So this after you minus this term with this term, then it becomes minus half of the beta, okay, root square of the h0. Now, like I said, I told you again, the linear has a limitation, so we can check how we behave if we compare, if we use a numerical method or the numerical technique to solve this number 8 in here, instead of using this this linearized form. So we can see how they behave if we just solve them, okay, using a numerical solutions. Okay, so if the one for the linearized model will generate you this curve in here, which is on the top of the nonlinear model in here, the curve A. Okay, so if you don't really go far away from this from the value, from the h0, then you'll be fine. The value will still be the same between the linear with the nonlinear model. Okay, but if you go far away, then of course the linear model the deviations will get higher, will get larger. The larger you deviate from that particular point, from the h0 point. Okay, so these are very important as we go with the time. So this is the time in here. Okay, because this one is a dynamic model, so it is a function of time. Now, we have talked about the linearizations. In order for us to make our life more simple again, we want to consider something that we call the deviation variable. So the deviation variable is actually the difference of the actual value of the variable from the steady state value. So like in this point, for example, this h0 is something that we take as a steady state value of the height. Okay. So if the controller of a given process has been designed well, instead of defining it in terms of the real actual variables, we can just express the process variable in terms of the deviations from the steady state value, because we want to control the control variables to be at the steady state value for most of the time, right? That's why the deviation variable model equations will be equal to the linearized dynamic model equations minus the steady state model equation. So how do we linearize using deviation variable form? So we identify the nonlinear term in the equation. We find the first order Taylor series suspension of the term around the steady state. We replace the nonlinear term by the approximate linear term. We subtract the steady state equation from the linearized dynamic equations. We rearrange it and write it in a simplified form. How do we do this thing? So it's always good to always go into the example. So we always go and check the examples. Okay. In this regard, hello Jason and hello Wong Yo. I just saw you just now. Okay, and hello Chising as well. So express the linearized model in example 5 in terms of deviation variable. Let Hs be the steady state value of the liquid level for a given value Fis of the inlet flow rate. So if we linearize model around Hs, then what we will have is eventually these equations in here. Okay, so instead of using H naught, we use Hs. So at the steady state, we will have this one becomes this term in here. Okay, when we substitute this Hs equal to this one, right? Then what we can do is we subtract these two equations. So this is the linearized model. This is the original model. So you put in this one around Hs, and then at steady state you put in these things. You subtract the steady state equation from the linearized dynamic equations, then you recover these equations in here. Okay, so if you define the deviation variables as in this regard, so the deviation in terms of the height will be you give this these things in here. Okay, you give this these things in here to differentiate this one between the deviations and the normal variables, and that's the same with the flow rate with the inlet flow rate as well. Okay, then you will be able to convert this. This is essentially equal to this one in here. Okay, so if you get that thing correctly, then this will be your final ordinary differential equation in terms of the deviation variables. Okay, then once you get these deviation variables, then everything can be solved easily using another tool that we call the Laplace Transform. This Laplace Transform is something that is very, very handy if we have linear ordinary differential equations. Okay, that's why this has been used very, very much in process control. This is the so-called Laplace Transform. So why? Because you can just simply convert. You use a Laplace transform to convert that ordinary differential equations into the Laplace form. Okay, you solve it in terms of the Laplace. You solve it in their Laplace form, and then you bring it back again into the real mathematical world. Okay, so this Laplace transform is defined as this one. So this you note that when we Laplace transform a certain functions, we put it in terms of the lowercase letter of f. Okay, then that Laplace transform of these functions will be a capital F, and then we have something that we call s in here. Okay, so if you want to convert a particular f in terms of the time, what you need to integrate the multiplications of that whatever that function is multiplied by the exponential of the minus st dt. Okay, this is the definitions of the Laplace transform. So the Laplace transform of a constant will be this one. So how did you do that thing? So this is how you derive that thing. You integrate from 0 up to the infinite. So what you put in a, right? You put in a. Okay, then the integrations of this e raised to minus s will be a divided by minus s est, integrate from 0 up to the infinite. Okay, so if you have the exponentials of the minus infinite, that will be equal to 0, right? And then minus a over s, if you put in 0 into this exponential, then that will be basically 1, right? So you need to go back into your calculus again. So that will be equal to the a over s. The same thing with the unit step functions. Okay, with the unit step function, you will have 1 over s. I will not go through the details in here. You can just go and inspect, and if you notice that I make any mistake, please don't hesitate to let me know, because I'm not free from mistake. Okay, so even though I have a PhD, but it does not mean that I'm much more smart than you guys. Sometimes I may make a typo as well that I need to rectify. So let's learn together in this regard. So if you notice that I make any mistakes or something is not clear in the derivations or in the process, then by all means, then you let me know, and then we check together. If I make a mistake, then I have to revise whatever I put into my lecture slides. Okay. It's the same thing with the Laplace transform of an exponential function. So let's say we have a Laplace transform of an exponential function. Okay. We can put this to substitute this ft. Now the thing is a bit longer, but since we are doing the same operations, we know that this will be 1 over s plus b. So the convenience of using the Laplace transform is that we don't really have to derive for everything. So we can come with the Laplace table that can give us a quick reference of what will happen if we just use a Laplace transform for a certain or for a particular function. So for example, for this one, if this is the Laplace transform of the derivative, for the first order derivative we have this, for the second order derivative we have this, for the n order derivative we have this, right? So table 1, this basically shows you what is the functions and what happens if we Laplace transform that functions. We will have this, okay? And then for this one we will have this, for this one we will have this, for this one we will have this one. This one I took the table from the old book of the Koganower, but this actually when I did my undergrad, this was the first edition, where the no Stephen L. Blank, only Donald R. Koganower and another guy called Koganower Koppel. That was a long time ago, I think about I did my undergrad at about 2000 until 2004, so it's almost 2 decades away. I think so. They always update this book. So this, if we have these functions in here, this will be the Laplace transform. Okay, if we have this sinus, they will have this transform. If we have a cosinus, if we transform, it will be this. Okay, and then if we have a sinus hyperbolic, we will have this. Okay. Note that there is a difference. If you just use a normal sinus, then you will have plus in here, you have negative in here. Okay, and then this is for the cosinus hyperbolic. This is for the exponential multiplied by the sinus. Okay, you have something that basically goes down with time. Okay, so this one is basically decay with time. Okay, then it's the same with the cosinus as well. And then this one is the unit impulse. You have 1 for this one. Okay, and this one is the one that I took from another book, Seborg, Edgar and Mellekamp. There are a lot of process control textbook out there, I think, and these two are especially the one that among the most complete table that I put into the slides in here. Right, this gives you a little bit of the of a view into the different form of the functions that you may have in here. Okay, and then this one as well, right? The references you can see in here. If you are interested with the book as well, you can download this book from the internet. or you can find it from the library as well in the page 42. Okay, this one is page 42 until 43. Now, after we have all those linear differential equations, we can solve them easily using the Laplace transform. The process in general involves the following step. So you would need to take Laplace transform of both sides of the equation. This can be easily accomplished using Laplace transform table. You rearrange the equation in the form of this fraction ZS, where you put in the numerator as ZS and denominator as a PS. And then you can use a partial fraction expansion to break equation from step 2 into simple fraction that can be easily inverted using Laplace transform table. Then find the inverse Laplace transform. So how do we do that thing? So these are some of the examples. For example, we have these linear differential equations with the initial conditions at time t equals 0. The value of the f will be equal to 1. Okay. So what we need to do is take the Laplace transform of both sides of the equation. So note that if we take in the Laplace transform of this term in here, it will be equal to this term in here. Okay, and then if we have a Laplace transform of the normal function, that will be equal to the fs. And then the Laplace transform of a constant will be a over s. So if we just do that thing, we will get these things in here. Okay, and then we can rearrange. We split the fs into the left-hand side, and then all the other terms into that doesn't contain this fs into the right-hand side. Okay, if we do these things correctly, we will have these terms in here. Okay, so this, if you go back again into the table 2, you see where you can find this Laplace transform. This df over dt will be this one, this st will be 1 over s. So your fs is this term in here. So what you need to do is you take the inverse Laplace transform using Laplace transform table. So you go into the table 2, and you notice that there is the similarity between these terms in here with this term in here. So this b3 will be 0.4, b1 here will be 0, and b2 will be 0.8. So what we need to do is we just put all this value in here into this ft in here. Okay, your b3 is 0.4, your b1 is 0, b2 is 0.8, b1 is 0. You put it in here, then you will get your ft equal to this term in here. Okay, so that seems quite straightforward for this one. Any questions so far, guys? Any questions so far, or everything is okay? I'm sorry for the background noise, guys. I'm at home. So if you get any questions, then you can ask me. If not, then I'll continue. Okay, partial fraction expansion is here. We talk about the partial fraction expansion. So these are the most common inversion method. The function to be inverted fs is merely rearranged into a series of simple functions. Okay, then each term is inverted by inspection since they are simple. Then the total time dependent function is the sum of the individual time dependent functions. So these are the good thing about the linear or linear differential equations, and why we do it with the Laplace transform. Okay, but of course in reality there is almost no things in real conditions that are actually linear. Most of the systems they are non-linear. Okay, so these are fs. Fs normally appear as ratios of polynomials. So this one is m order polynomial in S, and p is an order polynomial in S. And in here I'm taking it from the book of the Luyben, which is the process modeling, simulation, and control for chemical engineers. This is another textbook that are popular. Some people, they like Luyben because Luyben approach to process control is really practical. Okay, then we can factor the denominator into its root or zeros to give this. Okay, so you factor these things in here into these things in here. If all the pi are different, then fs can be expressed as a sum of n terms. It becomes this n terms in here. If all this 1, 2, 3, 4 up to the n terms is is different. Okay, then they can be expressed as a sum of n terms in here. The numerators of each of the terms in equation 10 can be evaluated as shown below, and each term can be inverted by using these things. So you can find A by simply putting the limit of S approaching P1, okay, by multiplying this S S minus P1 multiplied by your Fs in here. So if there are some repeated roots in the denominator of equation, so you can see the repeated roots, right? This is basically in terms of the roots, in terms of the square. So it's basically raised into 2. Then Fs must be expanded as a sum of n terms. Okay, so you have to expand this term twice. This is the first one and the second term in here. Okay, that means you need to have this expanded. The above is repeated order of 2. If the root is repeated 3 times, the expansion will be this term in here. So if you have the third order term in here, you need to account for it 3 times in here in your expansion. Okay, then this can be found using this particular equations in here, A, B, and C, for this particular terms in here, the one that is shown in equation 12. Okay, so I'm talking about this equation 11. Sorry, this one is talking about the equation 11. And for equation 12, then a second derivative will have to be taken. Then generalizing to the m term, then you have these terms in here, the generalized equations for this am. Okay. So if we just discuss it like that, then it probably gonna be a little bit abstract because there is no example. But the best way to make it clear is to bring it into an example. Okay, so resolve the differential equation example 7 by partial fraction expansion. So let's say you have these two equations in here. You take the Laplace transform of both sides into the equations, then you rearrange, you get this one. But since you can basically divide these terms with 5, divided this term with 5. If you divide this term with 5, then you will have S. You divide 2 by 5, you will have 0.4, right? You can do the same thing with here as well. So basically you divide the numerator by 5, you divide the denominator by 5. And you can see that I have a typo in here, right? I have an extra brackets in here that I need to move. I will do this after this lecture. Okay. If you divide 4 by 5, then you will get 0.8 basically. Then you expand into the partial fractions, you will get this. Right. If you want to expand into the partial fractions, then if you follow these terms in here, right, you just basically use this. You split this into this term in here, which is what you did in here. You split this equations into A over S plus B over S plus 0.8. So how did you find the A? So the A, you use the formula in here, right? You go with these terms in here. You multiply the denominator with the Fs. Okay, so you multiply S by this Fs. Then you equalize this S equal to 0, so you get 0.5. And for the B, that will be the same. Then you will get 0.5. Okay, so in terms of the partial fraction, you have these things. Then you can take the inverse Laplace transform using a table. So instead of us using a complex formula of this, what we do is we use a partial fraction expansion first, and then after we get the simple terms, so these two terms, then we can simply use the simple Laplace transform function. So we go back again into the original function. So for 0.5, 1 over S, we will get 0.5. For this 0.5 multiplied by 1 over S plus 0.8, we will get this one. So if we get these things, then we will get these equations in here. Okay. So now, if I'm not wrong, this will be the same way that we solve for these equations in here. Okay, except one way is you don't use a partial fraction expansion, and on the other example, you use a partial fraction expansion. Okay, guys, everything clear up to this particular point? Any questions that you would like to ask to me regarding the Laplace transform, so that we'll basically cover our week 2 process control. So I go a little bit fast last week because I want to cover in more materials, because I was unable to come last I think last Monday, right? I think so. That means I cover everything today. Okay. So tomorrow I think I will have that the process modeling, if not with you guys. Any questions so far? Alvin, Amanda, Clarence, Daniel, James, Jason, Juliana, Chising, Michael, Taha, Rachel, Selena, Tiffany, Yusi, Mongyo. Anything you would like to ask? No? Guys, the splash top has been registered for you. So I know you can go into your into the instruction that is given in the announcement. So you start on using that splash top in case you're not able to come physically. But if you want to come to the lab, also can as well. We already arranged for you to come into the lab if you want, and also you can use the Matlab Online. Okay. So how do you go into the Matlab Online? That's what I'm going to show you a little bit in here, so that you can start a bit early. So you click on the Matlab Online, right? You go into this, then you go into here, Matlab Online, right? Saying you click in here, start using Matlab Online. Okay, that's what you need to do. Then you sign in. You sign in using your Swinburne things, using your Swinburne. Then you should be able to do that thing. Correct? Everybody agree with me or not? Did you are you able to access this Matlab Online using your Swinburne account or not? Guys, anybody try this thing before, or you have your Matlab installed in your computer? So you have to use whatever the password that you use for your accessing your student account, or contacted Usha for this. So Amanda, you try. You can use this Matlab. So it's not doesn't have to. The good thing about the Matlab is that online is that you don't have to have a very high RAM in your computer, in your laptop, but instead this one is made into the cloud, so everything is being done quite easily in this regard. Okay, so you go into the Matlab Online. Okay, I'm showing you for the process control today. For the process modeling, I will find another time to show you again, but I have given you that the Matlab files, sim.cstr already. I hope all of you can access that thing already, right? If you cannot, then I try to put it in here. I drop your file here also for you guys to be able to do. Okay, so this one, this is basically your project one. Okay, this you can download. You put it into a folder, download, and then once you go back into your Matlab again, I have a lot of Matlab code in here, right? Because I'm teaching the process control and process modeling based on Matlab. So what to do now? How to run that thing? You go and you upload. You need to put in into which folder that you put in that thing, the sim.cstr. Okay. For example, if I put it in the download, then I put it in here, open in here. Okay, you uploaded this file already. Then what happened is that you click in here. You click on the sim.cstr to open that program first, and you have this common window in here, right? In the beginning, everything is basically clear. So whatever in Matlab code that start with the percentage symbol in here will not be executed in the program. Okay. The reason why we start the program with the clear and close all is basically we want to remove everything in the system. Okay, why? Because let me put h equal 1, for example. Then I will have that something in the workspace in here. Okay, so I have, for example, if v equal 2, right? I drag it up. So you see this, there is something in the workspace in here because I assign a value on that thing, correct? That put into your workspace of the Matlab. But if I put in clear, what will happen in here? See, I remove the values in the workspace. So this clear in here is basically same like if you have a whiteboard. You put in something in the whiteboard, then you remove everything, you clear it using this thing. So if in the beginning of the program, everything will be clear, close all, right? So if I want to remove everything in my common window, the other thing that I can put in is CLC. Okay, so that will basically reset my common window. So whatever that you have put into your current window, then this will have a tidy value like this, okay? Because this percentage value in here is given to a block of the coding to make it easy for the user of the code, and if in case they want to modify the coding later on. Okay, so this one easily you can just run. If you run these things, what it will execute is basically giving you a figure of your simulation, right? So these are the result of your simulations of the figure 1. This in here is the temperature of your reactor. This one is the temperature of your jacket. This one is the temperature of your is the flow rate of your jacket coolant. Okay, and this one is the concentrations of the A within your reactor. Okay, so let's say I want to play a little bit. Let's say I want to play a little bit in here. Okay, I want to play. I want to change a little bit on the conversion. So for example, I want to change it to 0.85. So you can change this conversion in here to see what is the difference if you put in 0.85. And then don't forget to change these things again in here. Okay, you put in, where is that reaction? So conversion is equal to F. You see the plotting, the plot table sprint conversion is equal to F TR conversions. Okay, subplot time F. Don't forget to always save again because you change. So after you change the variables and you save, then you run it again. You see what will happen with the conversion if you change the conversion, right? So this you clearly you see, if you change the conversions in here, this will be automatically reflected within your plot because the way that they write the code is such that they is automatically changed in here, right? So that comes from whatever it is in here. So this is TR equal to, what is it in here? Okay, and then conversion is equal to this, right? Step change of this gain. Okay, and then if you want to change the step change, for example, what is your step change in here? So let's say that one is the conversions, right? In the beginning we put in 330, for example, right? What you can do is, let's say for something we put it 320, we save it again, we see what's happening, how does it affect the reactor, right? So this will give you a little bit of the different terms in here, right? Then we can go into something. Let's go back again into 0.95 in the beginning, and then put it into 330 again in the beginning. Okay, then put a save first. Let's say we want to play a little bit now. Okay, step change. If instead of I want to put it instead of increasing the feed flow rate, we want to decrease the feed flow rate. What did I do? I can minus these things in here. So I save first. Okay, and then this means what I did is basically, when instead of disturbing it with the higher flow rate of the A, I reduce it I reduce. Suddenly at time t equal where the disturbance I apply, I reduce that flow rate of the A, because the disturbance in here is referring to this F in here, which is the flow rate into the reactor. Okay, and whenever we put in the change in the flow rate of the reactor, the controlled variables will be the temperature of the reactor. How do we control that thing? What we control is what we manipulate is the flow rate of the jacket. Okay, then you go and check again in here. This is the error signal in here. This is the OP. This is where the error signal will determine the operating points in here. Okay, and this things is basically just a logic to cap off the signal of the error. Okay, that is called the anti-reset windup. So we go into the details in here. So this stop is stopped at 3,600. So we can increase these things again. We can increase these things to, for example, 25 hours. For example, we can save in here. Okay. Then let's check where do we put in the disturbance. Let's see. Go. This one is the proportional value for your controller, 2.67. This one is the constant for your integral. So this one is basically using the proportional and integral controller, right? And this is the step change. This is just storing variables for the figure. This is the initial conditions and parameters. Okay, this one is the integration loop. This is the temperature controller. Okay, so we put in the disturbance at 900 seconds. So if I divide 900 by 60, meaning at what time is that we are putting 900 divided by 60. So 900 divided by 60, let me check into my calculator. Okay, so let's put in 900 divided by 60. So that things is applied at 15 minutes in here. If we want to increase it to something like, I don't know, probably 30 minutes. So we put in 30 multiplied by 60. So we put in 1,800. Okay, don't forget to save again in here. Okay, so you don't necessarily have to go into the details, but you need to understand which one is belonging to which one. So you'll be able to understand these things better. So what did I change just now? I just changed the disturbance and I just changed the time where that disturbance is coming on, right? So let's run it again and see if this code is working well for these things in here. Okay, so these are the results. So the disturbance is applied at 30 minutes in here. Okay, then that is what happened. So the temperature of the reactors goes back into its initial value. The temperature of the jacket goes up a little bit. The flow rate of the cooling is basically going down a little bit. Okay, and then the conversions of the reactor instead is going down. And you can see that this one is now 1,500 seconds, right? Or is that because I've only plotted at 1,500? That's what you need to check again in here. Okay, so that everything that is inside in here it has a logic, but if you understand how to use that code, then you will be able to utilize it for your project one. Okay, I think that's all. I think that's what I want to cover for today. So I'm just showing you how to put that thing into your Matlab Online, how to play with that code, and additionally, what you can do is you can also play along with this controller value again in here. What happens if you reduce this controller value? What happens if you increase that controller value, the proportional value? What happens if you increase this controller, this integral value, this integral constant for your controller? Okay, that is the thing that you're gonna learn in your project one with your group mate. Okay, if there is no anything else again, then I will let you guys go back into your lunch if some of you haven't had lunch. Just any more questions up to this particular point? Alvin, Amanda, Clarence, Daniel, James, Jason, Juliana, Chising, Michael, Muhammad Taha, Rachel, Selena, Tiffany, you see? Wong Yo, I just brief you in here ready, Taha. I just show you. You can go and go ahead and then you read by yourself your project one in here, right? I don't think I need to read all these things for you. I basically go into your things. So this is your system in your project one. Okay, you go into your canvas as announced already. This is the things. Okay, these are basically giving you an explanations of how this thing is operating. So this is a first order reversible reaction with this reaction rate constant. Okay, and the Matlab script is already given to you in the canvas already. Is that correct or not? Let me check. Is that correct? Supposedly, right? Supposed to be correct, right? If not wrong. If I go into your Swinburne canvas already, you should be able to access that thing already, right? So you can basically see how the code is working by putting it into your Matlab. You download the Matlab code basically, right? So where did I go and I check these things? Yeah? Should I show it to you or you guys already know, right? How to open that canvas already. If you have a problem in the canvas, then contact me or contact Hannah or Frederick, then we are always happy to help you on that regard, right? So let me go into the process control. Process control, where is my process control? Okay, so this is process control. Okay, now I need to go into the student view because I need to be able to see what you guys view, correct? So where is it being given? Is it being given on the week 4 activities? See this one? Okay. See this one? So this one is where you can download this Matlab code. If you click on this one, you will be able to see the SIMCSTR. Okay. This one you can upload into the Matlab Online and then start playing with that thing. So this is the definitions of the project one. Okay. Right. You can read on this one, and this is also giving you the due date. I've been quite generous. I give you by now already week 2, and you can start already from now to start on looking at these things. So so you can start ahead, and then this is the group list that we have decided on. Okay, this is the group list where you need to work with your friend on this list. Okay, and we don't really ask you to basically solve how the coding is. No, we don't. Okay, you read these questions carefully. We want you to derive the mass balance, component balance, and reactor energy balance. Okay, then a step change of 20%. Don't change the code that the way I do it. You don't. You just use the original code, and then you, depending on which group you are, then this is the assigned variables: the component A composition, overall heat transfer coefficient, feed temperature. You read these things carefully. Okay. Simulate and analyze the response at reactor temperature of 350 compared to the response obtained at this question. Study the effect of gain and reset time. Study the effect of step change on the system. Study the effect of two variables based on the default time tuning constant. And tell what happens with this in here. Okay, so this all is being taken from the book of Luyben in here, which I don't really need you to go through these things. Okay, but if you are interested, I already shared with you the book already, and just now I shared it in the Google folder. I don't know what's happening with my Adobe Reader. Sorry, yeah. It seems like it doesn't cooperate with me at this particular time. So you cannot see anything, but the book is already shared in there. So that one is in the chapter 3. The coding is there as well. Like if you want, you can see that thing. Okay. then that's it. So does that answer your question, Taha? Does it answer your question well or not? Taha, are you there? Is it clear enough for you? Oh, I can see you again tomorrow if I drop by into the tutorial. Oh, you are not in here, huh? You're online, right? So everything you can access already, Taha. Okay, so you all can just start right away. Well, we are going through the lectures, guys. If there is no other questions, then I think I will just conclude the sessions today, and then we see again on the process control next week. Tomorrow I will see you again on the process modeling. Okay, enjoy your afternoon, and it's nice to see you.